Hello everyone. In this session, we will be discussing multi-threading in parallel processing and multi-core computers of Unit 5. So multi-threading, we'll see we have different multi-threading options in multiprocessors. So the instruction stream is divided into smaller streams and we call it as threads, and they can be executed in parallel. And we'll see the wide variety of designs. So first, before we see, we'll see the definition of threads. So thread in multi-threaded process can be, may or may not be the same as software threads. So what is a process? A program in execution, we call it as a process. So it owns the resources, it owns the virtual address space, scheduling, execution, everything should happen. And when one program completes or is delayed and then another program should be executed, a complete process switch should happen. Now, what is a thread? So a thread is a dispatchable unit of work within a process. So it's a lightweight process. So it includes processor context, which includes program counter and stack pointer, data area of stack. And thread is a part of code which executes sequentially. And processor can run from one thread to another. That we call it as thread switch. And it is less expensive than process switch. So there are two types of multi-threading. One is explicit multi-threading and the other one is implicit multi-threading. So in explicit multi-threading, concurrent execution of instructions can happen from different explicit threads. It can be interleaved from instructions from different threads or shared pipelines or parallel execution or on parallel pipelines. So what is implicit multi-threading? Implicit multi-threading is concurrent execution of multiple threads extracted from the same single sequential program. Implicit threads are defined statically by compiler or dynamically by hardware. So we'll see how it gets executed. In the first diagram, we can see a single threaded scalar execution. So you have the processor program A gets executed, and when there is a delay or stall, processor waits and then it resumes with the same. The next is where you have interleaved multi-threading. That means you have more than one threads. A, B, C, and D are the threads. For each clock cycle, you have one thread that gets executed. So it is fine-grained. The processor has to switch between all the threads for every clock cycle. And if the thread is blocked, it can go to the next thread. And this process, you call it as interleaved multi-threading. The advantage is all threads get equally executed, but there are a lot of thread switches happening for every clock cycle. So you can go for another type of threads, explicit multi-threading, which we call it as blocked multi-threading. So this is a coarse grained, and you can see that program A or thread A gets executed, and when there is a stall, there is a thread switch which goes to then it happens to the next thread. So it is not every clock cycle has a thread switch. Only when a particular thread is blocked, the other thread will be switched and it gets executed. So you can avoid pipeline stalls. You can reduce the number of thread switches, and there is also concurrent execution of all threads. And we also have simultaneous multi-threading, where instructions simultaneously issued from multiple threads to your execution units of superscalar processors. So when there is a multiple issues, multiple threads each and every issue can have a separate thread. And then you also have chip multiprocessing. So processor is replicated on single chip. So each processor handles separate threads. So either you can have multiple issues in a single processor where each and every issue is a separate thread, or it can be multiple processors in a single chip. Each processor can have separate threads. So that is how multiple multi-threading, explicit multi-threading is designed. Thank you.